Ever wondered how AI systems now write code, diagnose diseases, or even create art? The answer lies in a revolutionary leap in neural network architecture, transformers. But what exactly makes them so powerful? Let's dive deep into the technical heart of transformers, unraveling their mechanisms, mathematical foundations, and why they've become the backbone of modern AI. For decades, recurrent neural networks, RNNs, and their variants like LSTMs dominated sequence modeling. But they had a critical flaw: sequential processing. Each token in a sequence had to wait for the previous one, creating bottlenecks for long-range dependencies. Then came transformers, introducing self-attention, a mechanism that allows models to weigh the significance of every token in a sequence simultaneously. This parallelization wasn't just faster, it fundamentally changed how we model context. Let's break down the core, the self-attention layer. Imagine a sentence like, "The cat saw the dog." Each word or token becomes a query, key, and value. The model calculates how each query interacts with every key, generating attention weights that determine how much focus each token should have. Mathematically, this is represented as attention QKV equals softmax, QKT slash square root DKV. Here dk is the dimension of the keys, scaling ensures stable gradients. This allows the model to dynamically assign importance, whether it's recognizing cat as the subject or dog as the object. But wait, how does the model understand word order? Enter positional encoding. Unlike RNNs, transformers have no inherent sense of sequence. So they inject positional information via sine and cosine functions of different frequencies. This enables the model to distinguish cat saw dog from dog saw cat without recursion. The result? A fully parallelizable architecture that scales effortlessly to billions of parameters. Now here's where it gets even more sophisticated: multi-head attention. Instead of a single attention mechanism, the model splits the query, key, and value vectors into multiple heads, each capturing different aspects of the data. For example, one head might focus on syntax, another on semantics. These are then concatenated and linearly transformed, allowing the model to learn complex hierarchical representations. This is why GPT-3 or BERT can grasp nuances like sarcasm or technical jargon. The implications are staggering. Transformers underpin everything from language translation to protein folding. In 2020, AlphaFold used transformer-like architectures to solve a 50-year-old biology problem. Meanwhile, models like T5 and BERT have redefined tasks like summarization and question answering. But this isn't just about scale. It's about a paradigm shift in how we model information, moving from rigid pipelines to flexible context-aware systems. Understanding transformers isn't just for researchers, it's for anyone curious about the future of technology. Dive into papers like "Attention is All You Need," experiment with frameworks like Hugging Face, or explore how these models are reshaping your daily tech. The next breakthrough could be just a few lines of code away. Stay curious and keep pushing the boundaries of what's possible. Thanks for watching. If you want to explore the math behind attention mechanisms or see real-world implementations, hit subscribe. The journey into AI's technical depths is just beginning.